When you fine-tune an AI model, you are destroying its prior knowledge. It's called catastrophic forgetting. But MIT just resolved it. They realized that the best way to fine-tune a model is through showing its smarter version to itself. So same model as a teacher and a student. It's called self-distillation. In this video, I'm going to show you what is this approach, which is very simple and I would say shockingly simple, and how you can apply it right now in your own projects. Let's check it out. Catastrophic forgetting. It's a known issue that you apply fine-tuning, it happens to your AI model. That means your AI model is going to be good on stuff or domain that you just did fine-tuning, but you realize that it totally forgot what it knew before very well on other domains or other skills or tools or tasks or whatever that your AI is being leveraged for. So what's the issue and how we can resolve it? Well, because you generally apply label data set and you're forcing the model to update itself or parameters through learning your fine-tuned label data, and you're sort of ignoring the AI model approach to learn or its own way to reason, then you are forcing it to be good on something, but unfortunately you're gonna lose the capabilities you have in other stuff. So that's what they call self-distillation, which is a new approach to mitigate this concern. As you can see on my screen, they actually applied this approach, which I'm gonna tell you what it is, and they realized that not only its prior task gonna be kept, like for example in base model was 66% accurate on sort of something in general base knowledge, let's say, without any applying fine-tuning. As soon as you apply supervised fine-tuning or SFT, you'll see that you suddenly have your accuracy getting deteriorated on prior knowledge. Although you made progress on new tasks, because in the new task it was 45%, now it is between 60 to 65%, so you got something with your fine-tuned data, but is now performing badly on other stuff, dropping from 66% to 56%. But SDFT, which is self-distillation fine-tuning, it's an on-policy approach, which I'm gonna tell exactly what it is, that let your AI model keep remembering, or it doesn't lose its own capabilities before that fine-tuning, and still you're gonna have even better accuracy on a new task compared to fine-tuning. So you can consider this self-distillation as a continuous learning fine-tuning approach, which is similar to RL. It's on policy, so it will learn with its own sort of way, which I'm gonna get tell more in details. But at the same time, it is also resolving that catastrophic forgetting issue, which is happening in supervised fine-tuning. If I want to really summarize what is this self-distillation fine-tuning, I would say this is something between supervised fine-tuning and RL. So it has best of both, comes together as middle. So let's talk about the differences of these three. You will understand self-distillation better. In supervised fine-tuning, if you follow my point on the left side, this is the way that you provide your label data. It's off policy. That means you just tell the model, this is the answer, this is the question, learn it. So there's no trial and test, there's no exploitation, there's nothing. So this gonna cause that catastrophic forgetting because you're enforcing the model to learn through your own label data. But in reinforcement learning, it is on policy. That means we have a reward function that will check if the model outcome is good or bad. So the model will keep revisiting that to improve itself through its own way on how to learn. So in reinforcement learning, there is no fine-tuned label data you provide as is. So the model has that flexibility to learn through its own way, through its own reasoning, because each model has been trained with different parameters, weights, and they have their own reasoning capabilities. So you have to respect that nature of the model when it learns by itself. So we have now on the other side here, self-distillation fine-tuning, which is a solution here we're discussing. What they do is that they take the same model. I'm not talking about a bigger model when we do distillation, as you might have heard about it. No, the same model that you want to fine-tune, use it as a teacher, and then the same model, you will use it as a student to teach it to learn. But here's a critical question. How? And how this self-distillation is different than general distillation. This is the secret sauce of the solution, which you'll find it very, very simple, but very effective. So what they do is that they take the same model, consider it as a teacher. They're gonna ask the same question. For example, explain what happens when ABC is happening. It's a prompt that you want to do fine-tuning. You ask the same question to the same model again, but as a student. But there's a difference between a student and teacher. When you ask the same question from both, A student is supposed to answer with no guideline, with no help, with no context. But when we ask the same question from a student, we provide some context, some few short examples, something that the teacher can cheat to answer you. So now, when we provide this same question to same model, but one time with context, one time without any context, the goal here is that the student model that had no context to answer should be ideally close to the teacher model, which is the same model but with some context. So as soon as we diminish that distance between this teacher and student, we are gradually letting our student model behave like teacher but without any context. So we are literally fine-tuning our AI model, but through this on-policy approach, because you're not providing specifically fine-tuned label data. So the model is learning through its own way. And they are actually, for that distribution differences, they're using reverse KL divergence, which is a formula that its goal is try to make sure that the distribution of the teacher answers versus student are as close as possible. This is really what we are optimizing here. So to take a closer look, when we use this reverse KL divergence, again, just one way of minimizing a distance between like these two distributions we're talking about, the goal here is that this function or objective function will penalize the student, the model that we're teaching, for placing a probability mass where the teacher has none. That means we're gonna make sure that the student gonna answer similar to the teacher, although teacher has context but student doesn't have. So this is really the approach that SDFT or self-distillation fine-tuning is doing. And the gradient is estimated over trajectory sample from the student, ensuring that we have this on-policy correction. That's why I'm sort of saying that this is sort of fine-tuning, a supervised one, but here with on-policy, which it's driven from RL. So it's a combination of reinforcement learning, stability, and no catastrophic forgetting versus fine-tuning, which sort of you're having this student model learning to get better and better with the approach that we provide here. So again, the teacher model will have some context, but what is that context? The context can be, again, some few short example or one question, one answer sample we provide, or just the answer. They actually try different approaches. They're going to talk about that shortly. But the goal, which is this intrinsic reward, because you know that in RL, we do have some sort of reward function. Sometimes it's very hard to specify what is a reward function to tell the model did good or not, because we don't know. It's a preference tuning that we're doing. But here what they specified is that, okay, we don't have any reward function, but we can specify that through, again, that distance of what model distribution of answers in teacher perform versus a student. So in base model, that student, we have no prior knowledge, but that teacher one, it has some conditional, or C here, conditional knowledge, which we call it some in-text. I would call it cheat for the teacher model to perform better. So the approach was simple, but does it really work in action? They started to testing out. So they tested out in different use cases like science Q&A, tool use, medical. They realized that when they applied their approach, STFT, compared to typical supervised fine-tuning or SFT, they saw that the base model is keeping its prior task performance without dropping or having that catastrophic forgetting, but at the same time improving itself to the new task accuracy. So in all different domains, when they tested, SDFT was certainly performing better compared to typical SFT. One interesting thing they tried is that when we do fine-tuning to introduce sort of a new knowledge to the model, which is not always the best way because you can potentially do RAG, but they wanted to see, compared to RAG, how this SDFT performed compared to also SFT. So they had this RAG function that could do 98% retrieval, and then 91% is the total accuracy of a model respond to you on a question that retrieve knowledge from somewhere. But if you do supervised fine-tuning on that data without any RAG, you can get similar answer but with 80% accuracy. But with SDFT, they got also better than SFT. So SDFT is helping you to also introduce new knowledge if you want to do fine-tuning for that. Of course, it's not as good as RAG, because RAG is retrieving exact knowledge coming into the prompt, so you're doing in context, few shots right in the fly. But it's still, compared to SFT, it is performing better, which is a major win for this approach on fine-tuning. This is one of the most interesting part of the paper that I want to probably walk through to you quickly. So they realized that, okay, let's do a couple of fine-tuning with our approach on different multiple domains or use cases to see if really the model will start forgetting its previous knowledge or not. And then we compare the same thing to supervised fine-tuning. So on the left side, which is their approach, they started to first train it on tool use. You can see that here on the tool use we have on the top. And as we are training a model on tool use, the tool use accuracy or performance of the model is certainly getting better and better. So it's a normalized performance. But then here, we are done with the tool use. We're gonna now start training the model on science. So on the science, you can see that suddenly this other blue line goes all the way up. This is science, but tool use is not dropping significantly. So still the performance of the model on previous fine-tuning use case was okay and not dropping, no catastrophic forgetting, and now this new domain comes up. Same thing, now this time we're gonna do train on medical. So these two are keep steady right on the top. They're not dropping their performance, just the medical tool use comes on the top because this is the third type of fine-tuning we're doing on the top of the same model. If you want to do the same thing but with supervised fine-tuning, you'll see that you suddenly start training on tool use. Okay, your tool is getting better, but other domains are suffering from catastrophic forgetting. Then you come here, you start training on science goes up, but immediately tool use that you just fine-tune that goes dropping back again because it is suffering from catastrophic forgetting. I think this chart perfectly demonstrates the capability of doing fine-tuning with that approach compared to supervised fine-tuning. Now, here's the critical question. If you got better model, bigger model, the approach really care about that or not? The answer is yes, it helps. So check this out. On the left side, they said that the performance gap between supervised fine-tuning, which is the orange one, compared to their approach, self-distillation, is getting bigger and bigger as we increase the model size. That means when your model is more capable, obviously that self-distillation performance is going to be even better because the model is more capable of learning, which is, again, learning from itself, the teacher of its own version. So, again, when you have increased the number of samples, you get better accuracy. When you increase the model size or capability of the model, you get better performance when you use self-distillation compared to supervised fine-tuning. Remember, I told you that the teacher model is the one that get the same question as a student get, but with some context. So what is that context? They try to have only answers as sort of that cheating context to the teacher, maybe just text or text and the answer together, and they realize that when we provide this text and answer, that's the one that we get better performance. And to give you some couple of examples, they provided some of their prompts in the appendix. Here's an example. So they wanted to actually fine-tune a model on some medical use case, for example, and they wanted to do self-distillation. So you can see that they have the initial prompt or ask that the same thing goes to the student, but this one has some question and answers, which are the context. So obviously the teacher gonna do better, but consider that teacher and a student here, they're exactly the same model, same version, same size. None of them in general is smarter compared to the other one, but we are just sort of providing a cheat code to one of them and the other one doesn't have, which is a brilliant idea and pretty simple. Here's the interesting part. One of the main reasons that supervised fine-tuning can cause catastrophic forgetting is that you're sort of killing the model capability to reason because you're enforcing it to do like your fine-tune labeled data. That's why sometimes when you do this supervised fine-tuning, the accuracy drop, and also the response rates sometimes drop because you're killing the performance of or the chain of thoughts. So what happens is that SDFT, their approach, it allowed the teacher to have that valid reasoning as they used to have with their own nature, so the model won't lose its thinking capability. That's why the response length in SDFT is keep getting maintained. So we are not really manipulating that. We're not affecting the reasoning capability of the model. We're just introducing what we're supposed to teach the model, which we don't see that in fine-tuning, supervised fine-tuning necessarily. So if you want to summarize that, that means what we found is the student or any model that you do fine-tuning must learn from its own generated trajectories to correct distribution shift. That's why this SDFT approach, which is sort of on policy, is performing better compared to typical offline distillation that we have seen with other models, and even supervised fine-tuning. This is really the secret sauce that let the model again learn from itself, but without we forcing it for labeled data, for cutting off the reasoning capabilities at all. So to summarize the benefits of SDFT, first of all, it's reward free. It's like you are doing reinforcement learning, but without the wrapping your head around what should be my reward function stuff. That's not the need anymore. It allows you to have that continuous learning. I showed you that with different domains, if you keep getting fine-tuning without cutting catastrophic forgetting, you can preserve your reasoning and capabilities of the model with the same approach. So the chain of thought gonna be maintained, which you will lose it in other fine-tuning approaches. It is scalable. That means as you have bigger models, we just discussed, the performance gonna be even better. And generalization. 98% accuracy on indirect knowledge queries. So having all this package in one place, I personally found STFT is certainly a great approach for fine-tuning models, but every approach comes with its own caveats, which I'm gonna explain that. So far, we talked about the benefits of STFT, but one thing you need to consider is that the training of this approach, the model through this approach, is slightly slower. So potentially you're gonna pay more, from 2.5 or up to 5 times more. You have to wait for the training job to be finished, so that 4 times more is something definitely considerable. You're gonna pay more for the compute, and you have to wait more to total wall time of your fine-tuning to get finished, so you're gonna potentially pay for your infrastructure. So again, obviously you're gonna cost more here, but the outcome that you get out of it might potentially worth, given that it's really tackling the shortcomings that you have in other typical fine-tuning approaches we just discussed. Alright, that was all about self-distillation, new approach just released by MIT. I hope you found this video helpful. If yes, I would be very thankful if you like and share your comments in comment section below, and subscribe so you won't miss the next video. Thank you so much.